Today we'll be talking about the Bohr atom, which is just simply a model of how the atom works. Now you hopefully remember that the atom is made up of three subatomic particles. The first is the proton, the second is the neutron, the third is the electron. The proton is found in the nucleus, the neutron is found in the nucleus, the electron is not in the nucleus. The proton is positively charged, the neutron has no charge, and the electron is negatively charged. The proton weighs 1 AMU, or atomic mass unit. So does the neutron. And for all intents and purposes, the electron has no mass. Because the proton and the neutron are both found in the nucleus, they are called nucleons. Now the atom is mostly empty space. Take, for example, a carbon atom. The radius of a carbon atom is 9/100ths of a nanometer, which works out to be approximately 4/1000ths of an inch. The radius of the carbon atom nucleus is about 3/1,000,000ths of a nanometer, which works out to be about 3/1,000,000ths of an inch. If you take those radii and compare one to the other, you see that in actuality, the overall atom is about 34,000 times larger than the nucleus. Now that's a big number. So let's try and put it into terms that you can actually visualize. Suppose we took a marble, just a standard marble, and placed it into room 611. Where would the edge of the atom be? It would actually be up the hill at Neighbors. Take a look at the map, and you can see right here where the marble is. Up here is Neighbors. That's about 2,900 feet. This would be the nucleus, a marble, and the edge of the atom would be here. That's quite a difference. Now there are multiple models of the atom. The one we're going to use is called the Bohr atom. In a Bohr atom, the nucleus is in the middle of everything, and it's really, really, really small. So we're going to use this red dot to represent a nucleus. The electrons go around the nucleus in what are called energy levels, and energy levels are given the abbreviation N. So you can have these circles that go around the nucleus. Each circle is called an energy level, and we number the energy levels starting from closest to the nucleus out. So this is the first energy level, this is the second energy level, this is the third energy level, so on and so forth. Now the number of electrons that can be placed on any energy level is limited, and it turns out that for any energy level N, the number of electrons happens to equal 2 times the number of the energy level squared. So for example, on the first energy level, N equals 1. The equation is 2 times 1 squared. 1 squared is 1. So you can place 2 electrons there, and that would look like this. Go to the second energy level. Here the equation is 2 times 2 squared. Well, 2 squared is 4, times 2 is 8. You can place 8 electrons on the second energy level. Go to the third energy level. You get 2 times 3 squared. 3 squared is 9, times 2. You can place 18 electrons, and you place them like this. And that's the maximum number. You can have fewer than that on an energy level, but you must fill the lower energy levels first. Also, the electrons on the highest energy level are given a special name, and they are called valence electrons. So here, the valence electrons are now in yellow. Valence electrons become important when we start talking about chemical bonding. So suppose you are asked to draw the Bohr atom for oxygen 16. The 16 is the mass number, protons plus neutrons. When you look at the periodic table, you see that the atomic number for oxygen is 8. So we know we have 8 protons and 8 neutrons. So we put down the nucleus, and in it we put 8p for 8 protons and 8n for 8 neutrons. Because this is a neutral atom, we have 8 electrons. We want to place those. You start with the first energy level. You can put at most 2 electrons there. 8 is more than 2, so we can definitely put 2 there. Once we've placed those 2 electrons, we have 6 electrons left to place. Go to the second energy level. On the second energy level, there is a maximum number of electrons that can be placed of 8. We have fewer than 8, so all 6 can go on this energy level. All the electrons have now been placed. So we can say that oxygen has 6 valence electrons. And this is the Bohr drawing for oxygen 16. So now I want you to do one. So please draw the Bohr diagram for magnesium 25. Remember, the 25 is the mass number, and mass number is protons plus neutrons. You're going to need your periodic table to find the atomic number. Stop, do it. I will then give you the answer, then walk you through it. Go. And your drawing should look very similar to this. Magnesium has an atomic number of 12, so it has 12 protons. 25 minus 12 is 13, so you have 13 neutrons. So we can place that in the nucleus. We now have 12 electrons to place. The first energy level will get 2, so now there are 10 electrons left to place. We can put 8 on the second energy level, and we have more than 8 to place, so we can now put 8 onto the second energy level. And so we have now placed 10 electrons. There are 2 electrons left, so they have to go into the third energy level. So the third energy level gets its 2 electrons, and we can now see that this is the proper Bohr diagram for magnesium. And if you're asked about the valence electrons, you'd say there are 2. Just follow the steps. So to review, atoms are small, and the nucleus is even smaller. The protons and neutrons are found in the nucleus. That's why they're called nucleons. So, obviously, electrons are not in the nucleus. They go on specific rings around the nucleus called energy levels, which are abbreviated N. You can number the energy levels from the nucleus outwards, starting with 1 and just going up by a whole number. The number of electrons that can go on to a specific energy level is calculated by the number of electrons on an energy level equals 2 times the number of the energy level squared. Any electrons found on the outermost energy level are called valence electrons, and the overall diagram is called a Bohr diagram. So with this information, you now know how to draw Bohr diagrams. Remember, this is just one of many models, but it's a very useful one and the one we're going to use in the course this year.